Today we'll continue approximating small chains. Okay. Let y be equals to f of x. And as x changes from x to x plus delta x, okay, fx changes from f of x to f of x plus delta x, change in x will be x plus delta x minus x. It would be delta x, okay, and also changing y values, it would be f of x plus delta x minus f of x, so it's equal to delta f, or it can be denoted by delta y. And that means delta y equals to delta y over delta x times delta x, and it will be del y over del x times delta x, okay, and it's equal to, okay, f prime of x times delta x. Approximation as delta x approaches to 0. And the relative change in x values will be delta x over x, we know that, and the percentage change in x will be (100) times delta x over x, okay, and let me give you an example. By approximating, by approximately what percentage does the area of a circle increase if the radius increases by 2%. Solution. Okay, and the total area, delta area, equals to del A over del R times delta R. This is the differences between the first and the second radius, of course, and we know that the circle's area equals to P times R square, okay, and after that del A over del R will be 2PR, okay, and the delta A, okay, will be 2PR times, okay, delta R, and after that, okay, 2PR, okay, over, I'm sorry, delta A over A, and A will be PR square times delta R, and the, okay, after that, when you simplify it, you will obtain the 2 delta R over R, okay, and if delta R over R, okay, goes to 2 over 100, which is the 2%, and then delta A over A, okay, it would be, okay, 2 times 0.02, okay, because of this part is this, and it comes here, okay, and after that we can say delta A over A approximately equal 0.04, and it's equal to 4 over 100, and approximately change 4%, okay. And let me give you another example. By about what percentage will the edge length of an ice cube decrease if the cube loses 6% of its volume by melting. In this question, ice is melting, and of course it loses some volume, okay, by the proving, and the what is the percentage, okay, and the edge of the cube. What can we say about the edge length of the ice cube, okay? And let me solve it. And we know that cube's volume will be, okay, and the length of h's cube, okay, and thus we know that delta volume, maybe same notation will be better, and it will be 3x squared delta x, okay, and we know that delta volume, okay, it equals to minus, okay, 6/100 volume. That's the total change, okay, and then we can say after that minus 6/100, and the volume was x cube, okay, and after that it's equal to minus 6x cube over 100, and we know that delta volume equals to 3x squared delta x, so 3x squared delta x, it equals to minus 6x cube over 100. So some simplifying them, okay, and we will obtain, okay, delta x, okay, equals to minus 2/100, okay, x, and after that we can say the edge of the cube decreases about 2%, okay, because here is minus sign. If it was plus sign, we can say increase, okay, but if it is minus sign, we must say decreases, okay. So let me continue with another subtopic, which was the higher order derivatives, okay. And we know that if the derivative y prime, which is equal to f prime of x of a function y equals to f of x, is itself differentiable at the x point, and we can calculate its derivative, okay, from the previous lectures. And now we can call the second derivative of f and denote by the y2 prime equals to f2 prime of x, okay. And let me give you some notation about this second derivation and the other high order derivation, okay. Let me give you firstly an example about this, okay, and the example, after that I will give you some denotions. If y equals to f of x, it's equal to x to the power of n, and n is a positive integer then okay, we know that from the power rule, okay, y prime equals to n times, okay, x to the power of n minus 1, and after that y2 prime it equals to n times n minus 1 times x to the power of n minus 2, okay, and it goes like that, and after that we can say y to the key, okay, and that means the kth derivative of y, n times n minus 1 times n minus 2 times, okay, and it goes like that, and n minus, okay, parenthesis k minus 1 times x to the power of n minus k, and if k is less than n, okay, and the generalized rule will be y to the kth derivative equals to n factorial over n minus k factorial times x to the power of n minus k, okay, if 0 is less than or equal to k is less than or equal to n value, and 0 if k is larger than n value. This is the general power of kth derivation. Example, find the nth derivative of y equals to 1 over 1 plus x, okay, or another saying 1 plus x to the power of minus 1, okay, and let's find its nth derivation. First we know that y prime equals to, okay, minus 1 times 1 plus x, okay, to the power of minus 2, and after that y2 prime equals to minus 1 times minus 2 times, okay, 1 plus x to the power of minus 3, okay, and from here we can say minus 1 factorial 1 plus x to the power of minus 2, and from this part we can say 2 factorial times 1 plus x to the power of minus 3, and the third derivation of y, it would be 2 times, okay, minus 3 times 1 plus x to the power of minus 4. So we can say for that minus, okay, parenthesis 3 factorial times 1 plus x to the power of minus 4, and then it goes on like that, and the last step of that, it will be y to the power of n equals to, okay, minus 1 to the power of n, okay, it will say us what is the sign of the total derivation. Okay, if it is odd, it would be negative, and if it is even, it will be positive. Okay, so n factorial times, okay, 1 plus x to the power of minus n minus 1. Okay, and this is the generalized rule of the derivation, which y was 1 plus x to the power of minus 1. Let's continue another example with another example, and find the nth derivation of f if f of x function equals to sine of ax plus b. Okay, don't forget chain rule for this trigonometric function. Okay, and the f prime, it equals to a times cosine, okay, ax plus b, and after that, okay, minus a square sine of ax plus b. Okay, and we can call minus a square times f, okay, because of the sine of ax plus b was fx. Okay, and that was the f2 prime, and the third derivation will be minus a cube, okay, cosine ax plus b, and it's equal to minus a square times f prime. Okay, right? And the fourth derivation, it will be equal to plus a to the power of 4, okay, sine of ax plus b, so it's equal to plus a to the 4 times f. Okay, and the fifth derivation, it will be, okay, and the plus a to the power of 5, okay, and the cosine ax plus b, so it's equal to, okay, and a to the 4th power times f prime. Okay, we can evaluate a rule, generalized rule for the nth derivation. After that, let me do that. Nth derivation of x, it's equal to, look at this part, okay, what can we say? We can say minus 1 to the power of k. Okay, it says us what's the sign of the total derivation, and the a to the n power, okay, sine ax plus b, okay, and the minus 1 to the power of k, okay, a to the n cosine ax plus b, okay, and for that if n equals to, okay, 2k, and of course k starts from 0, 1, 2 and integer values, okay, and if n equals to 2k plus 1, again k starts from 0, 1, 2, goes like that, okay, and for this generalized rule, these values are even value for n, and these are odd part, okay, of the generalized rule. Now we can continue with another subtopic, which was the implicit differentiation. Okay, and we know that the previous lectures, okay, and we can find the slope of a curve, which is the graph of function f of x functions, okay, and by the calculating or derivation of this f function, and we know that not all curves are the graphs of such functions, and we must graph of a function f of x, the curve mustn't intersect any vertical lines at more than one point, okay. And the curves are generally the graphs of equation in two variables, and such equations can be written by the capital of f x comma y equals to 0, okay, and we will say these are two variables, okay, and for that we will call these functions, okay, closed function. And what can we say about this closed function, okay, and this is interesting functions, and let's assume that, okay, y equals to f of x, okay, and after we can say f capital of f x comma f of x, it equals to 0, okay, and the y values depends on x value, okay, and the x is independent variable, y is dependent variable, and let me give you an example. Find the del y over del x if y squared equals to x, okay, and what's that function? We know that when you sketch it, it's also parabolic function, but it's like that, okay. xy, and what will we do? Okay, we know that we can say, okay, this closed function capital of f, it equals to, okay, y square minus x is equal to 0, okay, and after that we can call del over del x, okay, and the y square, it's equal to del over del x x, the second part of it, and we know that del over del y square times, okay, and the del y over del x, it's equal to del over del x, x will be 1, okay, and this part will be 2y, okay, times del y over del x, it equals to 1, okay, and after that del y over del x, which is y prime, it equal to 1 over 2y, okay, and for this function we can say, okay, and the y squared equals to x, okay, defines two differentiable functions, and the first part y equals to, okay, square root of x, which is the x to the power of 1 over 2, okay, and for x is larger than 0, okay, so del y over del x is equal to 1 over 2 times x to the power of minus 1 over 2, okay, and it's equal to 1 over 2 times square root of x, okay, and it's equal to 1 over 2y, okay. Please attention for this result, and let's take the second part of it, and it will be y equals to minus square root of x, and which is equal to minus x to the power of 1 over 2, and after that, for of course x is larger than zeros, okay, and del y over del x, okay, it's equal to minus 1 over 2 times x to the power of minus 1 over 2, and it's equal to 1 over 2 times, okay, minus square root of x, and it's equal to 1 over 2y, okay, and please attention for these parts, okay, these are same values, okay, these are all same values, okay.